A distributed system is a computing architecture where logically distinct software components are organized across multiple independent physical machines, acting together as a single service. Moving away from a single centralized computer creates a distinct paradox for engineers. On one side, physical distribution grants massive computational parallelism. You can process far more data simultaneously. On the other side, it introduces severe network latency and synchronization chaos. To understand how modern networks operate, we have to trace the evolution of system architectures, starting from isolated local servers, expanding into complex multi-tier networks, and finally examining the harsh mathematical realities required to keep these systems running when hardware inevitably breaks. Grasping distributed computing requires a shift in perspective. It is less about how a specific line of code executes on a CPU and entirely about how a collection of independent systems survives the hostile physics of a network. The capabilities of any system are dictated by its architecture. That structure defines the individual components, assigns their specific functions, and establishes the exact relationships and interactions between them. This diagram shows two primary architectural styles. On the left is the layered architecture, typically found in client-server setups. In the layered model, data passes sequentially down through adjacent levels to make a request and flows back up to deliver a response. The object-based model bypasses that vertical structure entirely, allowing distributed nodes to execute direct method calls to one another regardless of position. To see how this applies to actual machines, we look at the standard software stack. At the bottom layer, you have the local operating system managing fundamental resources. At the very top, you have the distributed applications the user actually interacts with, like email or FTP clients. This schematic illustrates the layer sitting between those two extremes, middleware. Notice how the middleware service stretches continuously across machines A, B, and C. Middleware serves as the essential connective fabric. It abstracts away the heterogeneity of the underlying hardware and the varying local operating systems, providing the applications above it with a single, simplified API to communicate across the network. The most basic way to organize these components is the multi-client, single-server topology. In this setup, local client machines handle the user interface, while a single, centralized server holds the data and executes the computational services. This chart maps the strict linear timing of that interaction. A client sends a request across the network, the server receives it, processes the task, and returns the reply. The critical flaw here is the wait for result phase on the top line. Because of network latency and the time required to provide the service, the user's local experience is completely paused. As user counts scale, the centralized server must handle every single request sequentially. It rapidly becomes an inescapable processing bottleneck. And because there are no alternative routes, a catastrophic single point of failure. To handle increased loads, engineers distribute the processing for a single service across multiple backend servers, as shown by the interconnected nodes in this diagram. This creates a chain reaction in the network. When a client invokes a request, the receiving server often lacks the complete data to finish the job. It must then act as a client itself, querying a secondary server to fulfill the computation. This offloading strategy led to the concept of the thin client. Devices like early PDAs or mobile phones lacked local compute power for heavy workloads. They functioned strictly to execute the graphical user interface locally, while the actual application logic runs on a remote compute server. Designing a distributed architecture requires deciding exactly where the computational burden should live, pushing processing logic to a remote server cluster, or keeping it on the local edge device. This schematic breaks down a three-tier system, using an internet search engine as the model. The architecture is explicitly split into a user interface level, a processing level for ranking components, and a foundational data level holding the raw database. Looking at the timing graph for a multi-tier setup, you can see how latency compounds. The application server cannot answer the user until it pauses to request and retrieve data from the separate database tier below it. This diagram illustrates that the dividing line between client and server is highly fluid. Depending on system requirements, the boundary can shift up or down the application stack, moving the database or application logic between the user's machine and the remote server.
If you erase that strict hierarchy entirely, you get a peer-to-peer or P2P architecture. Here, the traditional distinction between a client requesting data and a server providing it dissolves. Every single node in a true P2P network acts as both client and server simultaneously. Because there is no central authority, every application must carry its own internal coordination code to negotiate directly with its peers. Whether an engineer builds a rigid multi-tier cascade or a decentralized P2P web, the primary friction point moves away from maximizing pure CPU cycles and toward managing the precise timing and flow of network communication. Network performance is governed by specific metrics. Raw throughput measures the total number of jobs a system processes over time, but end-user response time measures the delay of a specific request. In large systems, engineers focus intensely on tail latency, the rare, exceptionally slow responses that can severely degrade the user experience. Optimizing this requires choosing the right type of parallelism. Fine-grained parallelism breaks tasks into massive numbers of small computations, requiring nodes to interact highly with one another, flooding the network with traffic. Coarse-grained parallelism uses larger computations with lower interaction rates, which is often much safer for network stability. Systems that operate perfectly with 200 machines will routinely collapse at 2 million. At massive scale, centralized routing algorithms, centralized directory tables, or single processing components inevitably choke under the weight of simultaneous requests. Even with perfect software, distributed systems are bound by physics. Every message exchanged suffers the inescapable delay of physical distance and protocol handling across fiber optic cables, slowing down local and wide-area networks alike. Because slow storage drives and long physical distances cannot be patched with software, systems must rely heavily on caching data locally and aggressively replicating databases to maintain acceptable speeds. This equation defines system availability. Uptime is maximized by increasing the mean time between failures, how long a component lasts, and drastically reducing the mean time to repair, how quickly the system recovers. This chart plots the hardware failure rate over time, resulting in the famous bathtub curve. Hardware does not fail randomly. It fails in highly predictable statistical patterns. Components exhibit a high failure rate immediately upon deployment, known as early infant mortality. If they survive this period, they enter a long, stable, constant failure rate before eventually spiking again as physical degradation triggers the wear-out phase. Because physical failure is an absolute certainty, engineers rely on the math of redundancy. If you deploy 4 file servers, and each individual server has only a 95% chance of being online, the probability of all failing at the exact same millisecond drops to 0.000006. The overall system reliability leaps to 99.9994%. Software redundancy operates on the same logic. Systems are programmed to expect code failures by structuring operations so that backup processes can instantly take over, or by using transaction protocols that automatically roll back a database to a safe state if a fault is detected. But this introduces the consistency dilemma. Replicating data across multiple global servers guarantees that the information remains available if one server dies, but it vastly increases the risk that users pull out-of-sync data if updates happen faster than the network can broadcast them. Furthermore, distributing resources across a physical network massively expands the security attack surface. Every new node and communication channel must be authenticated and protected against malicious data injection and denial of service attacks. System dependability is never achieved by trying to build perfect, infallible components. It is achieved by assuming everything will break, and by using mathematical redundancy to mask those inevitable hardware failures. The evolution from an isolated single server to a globally distributed architecture is an exercise in carefully managing complex trade-offs. Distributing a workload successfully eliminates centralized single points of failure and unlocks theoretically limitless processing throughput. But in exchange for that power, engineers inherit the unyielding physics of network latency, the complexities of asynchronous data updates, and the statistical certainty of component death. The ultimate goal of distributed architecture is to construct a system out of chaotic, fallible network machines and bind them together with middleware and mathematical redundancy so tightly that to the end user, it appears as one single immortal application.